Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much. It's a great pleasure to be here, and in particular I'd like to thank the organizers for doing such a fantastic job for organizing this conference. Our main motivation originated from physics, where in conformal field theory one is often interested in field theories with non-trivial B fields. And this has some sort of interpretation as derived equivalence of twisted sheaves. And Azumaya algebras correspond to twisted sheaves. There is a dictionary that takes you back and forth, which I have time later on I will explain. But they're equivalent objects, and that's why we were interested in studying moduli spaces of Azumaya algebras. We have several results on this moduli space of Azumaya algebras, but in this talk I will focus on a particular example which will tie together various ideas. So that will be the goal of this talk. So this is joint work with Colin Ingalls. Our archive coordinates are listed above. So the outline is I'll just set up the preliminaries, and then I will show you the construction of the moduli space, give the summary of the results, and then show how it ties to with the classical example due to Mukai. So, right. So just let me set this up. K is an algebraically closed field with characteristic 0. If you like, you can use complex numbers. X is usually a nice scheme, but you can, if you're not familiar with this language, just think of your favorite complex manifold. I'll define an Azumaya algebra in general, but then we will restrict to Azumaya algebras on K3 surfaces. So an Azumaya algebra A on a scheme X is a quasi-coherent sheaf such that satisfies two properties. A is locally free of rank n square as an OX module. So if you're thinking in terms of complex manifolds, just think it's a vector bundle of rank n square. And in addition, for all points in X where P is a geometric point, the fiber A sub P is going to be n by n matrices. So roughly speaking, if you have X, which is a complex manifold, then an Azumaya algebra on it is a vector bundle of matrices. So you have a vector bundle of rank n square, but it has additional algebra structure that fiber-wise it's a ring of matrices. Okay. Now the automorphism group of matrices is just PGLN, and this is, the action is by conjugation. So you just conjugate by an invertible matrix. So just like vector bundles correspond to elements in H1 with values in GLN, an Azumaya algebra, let's say if it has rank n squared, corresponds to an element of H1 of X, BGLN. Okay? So it's the same in analogy. So recall that vector bundles are in H1 of X GLN. So just to give you an example, suppose you have a locally free sheaf or a vector bundle, okay? Then just take V tensor V dual, which is endomorphisms of V, and this is an Azumaya algebra. So Azumaya algebras, which are endomorphisms of vector bundles, we're going to consider as trivial. I'll explain in a minute why. We're not as interested in them, but they're handy as an example. The other thing I want to say is that two Azumaya algebras are equivalent. So A is equivalent to B if there exist locally free sheaves, or let me just say vector bundles, such that endomorphisms of V tensored with A is isomorphic to and W tensored with B. So if these two things are isomorphic as Azumaya algebras, then we say that A is equivalent to B. So since I'm on the roll with definitions, I might as well define the Brouwer group. I might not use it later, but I might. So the Brouwer group of X is just going to be all equivalence classes of Azumaya algebras on X. It's a group with the group operation being a tensor product. So I'm sorry I didn't mention that before, but if you take one Azumaya algebra, if you take one Azumaya algebra A and another one B, then you can create a third one by taking A tensor B. So they actually form a group. And with this equivalence relation, note that and V is equivalent to the structure sheaf or the trivial bundles. So that's why we call these trivial, therefore. And all Azumaya algebras of this type are called are trivial. Okay, now I need to define one more thing. We have a short exact sequence in cohomology, well, étale or analytic, whatever you prefer. So mu sub n denote the nth roots of unity. So this embeds in the special linear group, projects onto PSLN, which is also PGLN to 1. And this leads to a long exact sequence. Okay, I'll just denote some terms. So H1 of X UN, H1 of X SLN to H1 of X PGLN to H2 of X UN. And here we stop. So let's call this map delta. So if you have an Azumaya algebra, the image of A in H2 of X with values in UN is called the underlying gerb of A. Okay? So delta of A is the underlying gerb of A. You can think of it, I'm not going to write it down because this is being recorded. You can think of it as a Chern class. I mean, all the Chern class of an Azumaya algebra is always trivial, but it has this particular class in second cohomology associated to it. So, just roughly, you can think of it in that context. Okay, so now I've set up what I wanted to set up, and I'm going to go on to the construction. So, let's say you have 3 rank 6 symmetric matrices. You can think of these as quadratic forms on the rank 6 vector space on K6 or C6, whatever you wish. You take the associated quadric hypersurfaces in P5. So, for example, just to set up the notation, say you have this vector in K6, then the quadric Q0 is the set of all y such that y M0y transpose equals 0. So that's what I mean by the quadric hypersurface defined by this. And then you now generate a family net, or what we call a net of quadrics, spanned by Q0, Q1, Q2. So what is this? this is so this is contained in P2 cross P5, and it consists of the set of all points A, Y, such that Y A0 M0 plus A1 M1 plus A2 M2 transpose. So this, so we're okay. Sorry, I forgot to say a point A in P2 has coordinates, homogeneous coordinates A0, A1, A2. So this now defines a family of quadric hypersurfaces in P5 parameterized by P2. So we can think of it as a quadric bundle on P2. So Q is a quadric bundle on P2. So, and let's say Q restricted to a point is going to be a quadric hypersurface in P5. Okay. So some of these are going to degenerate, and I just want to specify that because that will be important, an important assumption. So which ones will degenerate? Well, precisely those for which the determinant of this matrix vanishes. So this is a matrix with linear entries in the AIs, and wherever the determinant vanishes, that's where the quadratic form will degenerate. So I'm going to call the vanishing locus of these quadrics, I'm going to call it a curve C. It's going to be a degree 6 curve in P2. Okay, and important assumption for generic choice of Q0, Q1, Q2, the degenerate quadrics have rank 6. No, sorry, 5. So what I mean is that the quadrics, so i.e. the singular locus is just a vertex, a point. Okay, so now once you have a quadratic form on, say, V, a vector space, then you can form its Clifford algebra, well, Clifford CL of Q, which is just to take tensor powers, direct sum of tensor powers of the vector space, modulo the relation V tensor V equals Q of VV. Okay. Now this, so the even degree terms form a subalgebra which we call the even Clifford subalgebra. So this is the subalgebra of even degree terms. So this works for non-degenerate quadratic forms on vector spaces, and we want to generalize this notion to a family of quadratic forms which do degenerate. So now, for instance, in that case, so there isn't really a notion of a Clifford algebra for this family of quadratic forms, but so let me write this down as Q as a quadratic form on the trivial bundle O6 with values in the line bundle O of 1, P2. There isn't a notion of a Clifford algebra, but we can form a sheaf with an algebra structure which we call the even Clifford algebra of Q. And the definition is technical, so I'm going to skip it in the interest of time. But all I want to say is that for all practical purposes, wherever the quadratic form does not degenerate, this coincides with the usual notion of the even Clifford algebra. Okay? I can explain the technical terms later on if you like. So, so the point is now we have this family. Let me draw this here. So let's say this is my P2, and let's say this has this curve C, and away from C. So if I pick a point away from C, then the even Clifford algebra of the quadratic form associated to A is going to be a direct sum of 2 copies of 4x4 matrices. Okay. So to understand what happens when the quadrics degenerate, we have to do a calculation over along a slice transfers to the sextic. So now I'll draw another picture, which is as follows. Okay. So it's enough to do this computation locally. Okay. So let's say here is your curve C, and you cut across it with a disk, let's say with parameter t, and this is where t equals 0. Then what we do know is that if we pick a point here away from t equals 0, then we get 2 copies of 4x4 matrices. So what happens when we cross the sextic? So it's enough to do the local computation, and locally this quadratic form can be written as the diagonal matrix, the identity I5 with a t at the bottom. Okay, so when t is 0, this degenerates. When t is not 0, this doesn't degenerate. And then we do a computation. We calculate that CL0 of Q locally is going to be 4x4 matrices over K adjoint square root of t. So this gives the so the standard theory of Clifford algebras is for quadratic forms which are not degenerate. So we have to use some tricks, and we have to use some standard, we have to adapt some methods to actually do this computation. But then it turns out to be quite nice, where you can see that this is a family of matrices living on a double cover branched along the sextic. So you get branching behavior over here. So over the sextic you get 1 copy of 4x4 matrices, and everywhere you get 2. So in other words, theorem, so if you take M to be the double cover of P2 branched over the sextic C, then the even Clifford algebra of this quadratic bundle is an Azumaya algebra A on M. So it lives on the double cover. We then went on to calculate its invariance, and for that we had to use the theory of Koszul algebras and then some techniques from geometry. And the Euler characteristic is 2, the Turing class is 30. But most importantly, we found that H1 of A mod O is 0, which means A has no deformations. So it doesn't deform. It would be interesting to know whether this is the only Azumaya algebra in its equivalence class, if there are others. But anyway, there is no higher dimensional moduli space for this. But what we can do is we can do a reduction to get a family of Azumaya algebras which do deform. So let's do.
Your local calculation is saying that even over the degenerate locus is still an Azumaya.
Yes. Yes. So it lifts it lives as an Azumaya algebra on the double cover. Yeah.
So if you take the Clifford algebra of a degenerate quadratic form, you're saying something like that still splits into an endomorphism algebra?
Yeah, so there is a technical assumption here. I mean, I'm assuming my sextic is smooth. My degeneracy is not too bad, So in this particular case, it does, yes. But if there was higher order degeneracy, I don't know what would happen there. But for this particular case, yes, it still does. It lives as an Azumaya algebra over its center, which is a double cover of the original plane. Yeah. Okay. So this guy doesn't deform. So let's try to do something else. So let's take the base locus of my net of quadrics, which some of you will recognize. X is another K3 surface of degree 8 in P5. And you choose a point X in X. And now you just project away from X. So what do I mean by that? When A is not in the locus of degenerate quadrics, then you take the tangent space at x to q sub a, intersect with q sub a. This turns out to be a quadric cone over a smooth quadric surface. So this is a smooth quadric surface. This is your x. And so when you project away from x, you get a quadric surface in P3. So this is cone over smooth quadric surface. When A is in C, okay, still things are still not too bad. You get a cone over a quadric cone now. So your quadric surface has degenerated, and because my assumptions were, they're the generic case for which the degeneracy isn't too bad, you still get, the surface is not too bad. The quadric surface is not too bad here. So again, by projecting away from x, you get a family of quadric surfaces. So you get a quadric surface bundle. Whoops. Over P2. This depends on your choice of point x in x. But now the thing is, the neat thing is that this family of quadric surfaces doesn't live in a P3 bundle. It actually lives in the projectivization of a vector bundle, which we compute. So we calculate what that vector bundle is. So theorem. So let me call this family Q sub x. So Q sub x is a quadric bundle on omega 1 of 1 direct sum O2 with values in the line bundle O of 1, and the degenerate locus is still C. So degenerate locus is C. And now you can take the even Clifford algebra associated to this quadric bundle, and then we get something that I'm going to call B sub x. And B sub x is a rank 4 Azumaya algebra on M with Euler characteristic 0, C2 equals 8, and it has deformations. So we adapt some results of Artin and Lyon to show that the moduli space of the Azumaya algebra is Morita equivalent to B sub x, and with the same underlying gerbe is a smooth projective surface. So moduli space is A. So it's a slightly technical result, and I don't have time to go into it, but I'm happy to answer any questions you have. Smooth projective surface. Question is, what is it? So notice we did this reduction by choosing a point x in x. So if you take an x in x, you get an algebra B sub x over M. And so this gives a natural map to the moduli space. And then the question is this map injective? And there's no direct way of showing that if you take two different points, the Azumaya algebras that you get are actually not isomorphic. So we had to work around it a bit and go to the Brouwer-Savary varieties and show that the orthogonal Grassmannian of this family of quadric surfaces is isomorphic to the Brouwer-Savary variety of the associated Azumaya algebra. So the orthogonal Grassmannian max. So what is this? This is the variety parametrizing rank 2 left ideals in B sub x, and this is the variety of maximal isotropic planes. Tropic, or just isotropic planes. Isotropic planes. So this is the conic bundle. This is actually a conic bundle that lives on M. And then you can show that, well, if x is not equal to y, then we can show that the Brauer-Severry variety of B sub x is not isomorphic to Brauer-Severry variety of B sub y. And then again, we have to use some tricks, and we use the result by Newstead to show that B sub x is not isomorphic to B sub y. So then this gives it to us that actually x is isomorphic to the moduli space, because this is smooth projective surface, x is a smooth projective surface, the map is injective. So everything works nicely. So in the last 3 minutes, I'm going to try and explain the relation with Mukai's classical correspondence. So I did cheat a little bit. Let's say you start off with 3 quadric hypersurfaces, then and assume that the Picard rank is just 1, then the moduli space of rank 2, so first Chern class, the hyperplane section, and second Chern class equal to 4 is isomorphic to M. So Mukai has written down this correspondence. He didn't exactly write down the proof, but I'm sure he knew it. So, but if when the rank of the Picard jumps, then you have to be a bit careful because stability conditions change. And then there's some work to be done, and it's not always true, but it's true in this case. So M, the double cover of P2 branched along the sextic, is naturally a moduli space of vector bundles on X, but it does not work vice versa. So what is X? How would we characterize X? Well, X is so the thing is, starting with an X, there is a unique double cover of the plane, but if you start with a double cover of the plane, there isn't a unique corresponding K3 surface, which is the base locus of a net of quadrics. You have to make a choice. You have to choose a theta characteristic, an even theta characteristic on C, take its symmetric resolution, so that gives you a 6 by 6 matrix with of linear forms on P2, and that defines a net of quadrics. Let me call that matrix. L, whoops. And then this gives you a net of an X, a net of quadrics. And you do have a lot of choice for the generic curve, which is degree 6 in P2. There are 2 to the 9 times 2 to the 10 plus 1 choices of such an even theta characteristic. So you get these many families of non-isomorphic Azumaya algebras. And now I will state just our theorem in the last minute, which is that, oops, I don't know if you can see. If you take the double cover of the plane, choose an ineffective theta characteristic on C, take the associated net of quadrics, take its base locus, then that X is going to be a moduli space of Azumaya algebras on M, which have Euler characteristic 0, second Chern class equal to 8. And so it's something like an inverse of the Mukai correspondence. And then the second theorem is about a derived equivalence, which it's a natural theorem, the second one. It's not too surprising, and it has been formulated in terms of twisted sheaves already. But it's nice to have a concrete realization in terms of Azumaya algebras. So you take X and M as above, you take B, a rank for Azumaya algebra with the same Chern constraints and Morita equivalent to any one of the B sub X that we've constructed above, and you take the derived category of left B modules on M, then the derived category of B modules on M is equivalent to the derived category of OX modules on X. So there is a derived equivalence as well. And actually we prove a more general result, but I just stuck to this particular case because I'm talking about this in this talk. But we prove this theorem for cases where M is a non-fine, where 1K3 is a non-fine moduli space of sheaves on others. This theorem incidentally has an interpretation in terms of twisted sheaves, and that has been formulated and done. That's work of Calderaro, Yoshioka, Hoibre, Stellari, and so on and so forth. So I think that's where I'll end. I'm sorry I didn't get to explain the relation of twisted shoes, but I'm happy to do that afterwards.
Any questions? Okay, but thank you.